Hi everyone, I'm going to go through an example of a bond energy calculation, which I know that some people found a little bit difficult. No matter how you approach these, they're all exactly the same. We're looking here at bond dissociation energies. Now the word dissociation, which you can see just here, just means to break. So if we're dissociating a bond, we are breaking it. Sort of pulling the atoms apart and breaking that bond. So don't worry too much about that word, it just means to break. So the question says, methane reacts with chlorine in the presence of sunlight. The equation for this reaction is shown. Some bond dissociation energies are given in the table, and we have here the bond dissociation energies. Now remember, the unit is kilojoules per mole. A mole, remember, is just a way of measuring molecules in the same way that a dozen is 12. A mole is a very large number of molecules, but is always the same number of molecules. And if you want, you can just think of this as being kilojoules per molecule if you like, although that is technically wrong. All of these are data values that we would be able to look up in a table. They would be the same wherever we look, maybe to a slight difference in the number of significant figures, etc. The question says, show that the enthalpy change delta H for this reaction is minus 103 kilojoules per mole. So we have a show that question. That means they've given us the answer to work towards, which is quite nice, but it's 3 marks and we have to show all of the steps of the working. Now these exam questions are normally 3 marks, whether they give you the answer or not. If you get the correct answer, if it's not a show that question, if it's a calculate, if you get the correct answer, you get all 3 marks. But if you get the answer wrong, you lose all of those 3 unless you show the working clearly. So these steps are really important, and this show that question really does show that. That's not a pun. Delta H, well, that just means change in enthalpy, and enthalpy is just a particular sort of scientific way of saying heat energy. So delta H just means change in. That triangle there is delta, which is change. So let's have a look at this question then. So the first thing that we need to recognise is that we need to work out delta H. And delta H is equal to the energy at the start minus the energy at the end. Now that would be a sensible way of working out change in energy. And we could also be a bit more precise and say the sum of the bond energies of the reactants at the start minus the sum of the bond energies of the products, but we can just be simple and say energy at the start minus energy at the end. That is fine. If we were doing A-level, we'd want to be a bit more specific. So let's have a look at the information that we have. The energy at the start then is going to be the energy of the bonds in the reactants, which I've highlighted just there in yellow. So what bonds do we have present? Well, first of all, we can see that we have CH bonds just here in the table. Now, how many CH bonds do we have? We have 1, 2, 3, 4. Now, I'm using a highlighter there just to highlight the bonds so that I know that I've counted those bonds, okay, and I've not missed any out. It's very common for people to miss them. What other bonds do we have on that left-hand side? Well, we have a Cl to Cl bond, which I've just put there in green. So now that we've looked at all of the bonds that we've got, we can start to calculate these. Now we said we had 4 lots of CH bonds and we have 1 lot of Cl to Cl bonds. So 4 lots of the CH value, which is 413, would be 1,652, apologies, and the Cl to Cl is 243. So I'm just going to go straight in and put 243 there. Okay, so to break all of the bonds on the left-hand side, we would need a total of 1,895 kilojoules per mole. And that is the energy that is stored in the reactants, and therefore will be the energy to break the bonds in the reactants or to make them. But in this case, we are breaking these bonds. And that means that we need to put energy in. Okay. Now, if we were to look then at the energy at the end, okay, that is the energy that is stored in these products. And if we look here, what bonds do we have? Well, again, we have CH bonds. There's a CH bond, and then we have 2 more. So we have 3 CH bonds. So I'm going to write that straight away. I'm going to put 3 times C to H just there. Then we have a C to Cl bond. Okay, so we've got a different bond this time, so I'm going to put 1 times C to Cl. Do we have any Cl-Cl bonds? No, we've got no Cl to Cl bonds, so I'm not going to highlight anything in green. But what we do have is we have an HCl bond, HCl there. Now, it would be exactly the same if it was HCl or ClH, and we can see that from the carbon to hydrogen bonds. It doesn't matter if we've got C to H or H to C, they're both exactly the same thing. So what did we say? We have 1 H to Cl. Now I've put those in line with the table, but it doesn't really matter. You can put those in any order. So 3 lots of 413 for our carbon to hydrogen bonds would be 1,239. The C to Cl bond is 327. And our HCl bond is 432. So this is making bonds. And that means that we have energy out. That's always the process. So we need energy into the system to break the bonds. We're going to get energy out. So what's the total energy that we get out of this system? We get a total energy of 1,998 kilojoules per mole of energy being released from this reaction. So there we go. We can do a simple show that reaction. The energy at the start was 1,895. We're going to minus the energy at the end, 1,998. And if you pop that into a calculator, it comes out as 1,000 minus 103 kilojoules per mole. Now, where do the marks come from? The marks come from calculating the energy at the start, calculating the energy at the end, and then taking one from the other. It doesn't actually matter which way round you do this. If you did 1,998 and you took away the 1,895, you would get 103. So you'd get the same size of change. 103. So you'd get the same size of change. Now it's not a negative, but the negative here, this negative is not actually to show it's a negative number. That is to show that the energy is being lost or given out. So that's why a negative delta H, that's why we've got a negative delta H just here. So if you, whatever way round you do this taking away, if you say energy at the end minus energy at the start and you get a bit confused, do always just double check. Do you have more energy being given out or do you have more energy going in? If there's more energy coming out, then it is a negative. Now, if you have any questions on that, do please let me know, get in touch. You don't have to do all the highlighting, you don't have to do the extra scribbles. The bits that you need to do, okay, to show the working are calculating the energy at the start, calculating the energy at the end, and then doing the overall calculation to get the answer. Now you can go straight into doing this bit at the bottom here and not do the working at the top. However, that is just going to get you into a pickle if you do make an error. It doesn't make it clear necessarily exactly what you're doing for the examiner. So the bits I've put in the purple circles there, that's sort of like the perfect working. Now something else I just want to point out while I'm here is that you might notice that we've got 3 C to H bonds on the right hand side being made, but we've broken all of the 4 CH bonds on the right. And some people might say, oh, okay, well, we can do a shortcut and we'll ignore all of the CH bonds on the right hand side and we'll sort of cancel them out. Now, I'm not going to go into any more detail about that, but I'm going to say to you, avoid cancelling out. Okay, so if you've spotted that shortcut, avoid it. Okay, now if you haven't spotted that shortcut, don't worry at all about what I've just said. Okay, as I said, any questions, let me know, get in touch and I'll help you as much as I can.